Hello, everyone. This is John from Arctech Solar. I'm the director of technical support. Well, first of all, I have to apologize to the my audience. I was in 7 days quarantine, so not have a chance to change my clothes. But I think it's okay. You are not coming to looking at my pretty face. So let's focus on the my presentation today. I'm talking about the challenge of designing a tracker for the large size solar modules. First of all, let me introduce the Arctech Solar to the people that are not familiar with Arctech Solar. So we are a tracker company, and we founded in 2009. The headquarters is in Kunshan, Jiangsu province. We have been listed in the IPO on 2020, and we are the only one tracker company that in China to go to IPO successfully. And we ranking the top four global market in the tracker industry, and we're also the top one in China and India and Asian Pacific for many years. There are lots of offices around the world, and we can provide the service all day long. Up to the end of 2021, we have done 30 gigawatt globally for the tracker. Okay, so let's start today's topic. The large size solar module challenge. Back to the 2019, end of 2019, we saw a big new changing of industry that the solar panel size is increased. We have summarized several top solar suppliers size of a panel. This is the picture. This is the map of the length of a panel. And we saw the length of the panel increase from the traditional 2 meter to the 2.2, 2.4, or even 2.5 meter. And the width of the panel increased as well. So before it is about 1 meter, and now it is 1.1, 1.3 meter. So the size of the panel increased, and we know that the tracker is a structure, design. So for the structure design, the dimension is a key. And if the size of the panel increase, it means the tracker's 4 dimension. There's a 4 dimension of the tracker need to be increased as well. The first one is the curve, and second is the span. The span is the distance between 2 posts. The third is the height. The tracker height will increase. And the fourth is the length of the tracker. The tracker become longer and longer. Okay, so what is the challenge if this panel size increase and the tracker dimension changes? The first challenge is the panel length will increase, will change the tracker design. Before talking about the panel length, let's looking at this formula. This is the most important calculation of the tracker. This is the wind load calculation. So if we want to calculate the wind load, we have to, let me see if I can use the, okay. So if we want to calculate the wind load, the first step is to calculate the basic pressure. Okay, and the basic pressure including the air density, velocity, importance factor, height factor, topographic factor, directionality factor. And all these factors is related to the project itself. And once we have the basic pressure, we have to multiply the 2 more factors. The first factor is called the Sharp coefficient. Also, we call it pressure coefficient. And this is from the static, wind tunnel testing. And the second factor is called the DAF, dynamic amplification factors. This is from the dynamic testing of the wind tunnel. Okay, and once the size of the panel, especially the length of the panel changes, the so-called characteristic, dimension changes. And once it is changed, the pressure coefficient will change as well. Because, since the size of the panel changed, the turbulence of the panels will increase. And that will increase the dynamic load of the the tracker, dynamic load of the wind. And the dynamic load of the wind PD increase means the GCN increase. Okay, so panel length increase, the GCN will increase as well. Since the tracker itself, most of the tracker need to go to wind tunnel testing to do the tests. And the wind tunnel test has two purposes. Okay, the purpose one is to verify whether the tracker is stable, whether the tracker is okay. The purpose two is to achieve the data, and based on the wind tunnel testing data, we will calculate the wind load. And since the size of the panel changes, the data itself will need to be reflect, because the data has its limits. Most of the wind tunnel testing data has its limits. Before, the limit is a 2-meter panel, and now we are talking about 2.5 or 2.4 meters. So the limits of the wind tunnel testing need to be refreshed. So we have to done lots of the wind tunnel testing again to achieve the large size panels data. In end of 2019, before the large size panels change, Arctech, found out there maybe have some change on the size of the panel, and we are collecting data and ask the CPP, which is the most famous, wind tunnel consultant, to redo the wind tunnel testing for our production line. And currently, for our two product, the 1P Skyline 2, our range of wind tunnel testing data could be from 1.8 to 2.7. And our 2P system, the SkySmart 2, could be used for a panel size that including from 1.9 to 2.5. That means, in the industry, in the current industry, our two product can be used for all kinds of panels. However, the other trackers, they have to redo the wind tunnel testing, and before they finish the wind tunnel testing, their data could be only used within 2.2 meter. Okay. And after the testing and after analysis the data, we do a comparison. We want to understand how much load increase, how much coefficient will increase if the size of the panel increase. So if you look at these three diagram, you will find out that compared to a traditional 2-meter size panel, a 2.3 meter size panel will increase the coefficient from 4% to 11%. That means, if we're talking about the same velocity, and the pressure will increase up to 11%. So that is a lot. The second challenge is, the panel width increase, and that will change the tracker design. Before talking about that, challenge, let's look at the mode of tracker. There are three different modes of the tracker. The mode means, if the wind hit the tracker will deflect, right? There are three different ways of deflection. So the first one is called the torsional mode. The tracker itself will twist it along its axis. The second mode is called the heavy mode. The axis will moving up and down. And the third mode is called swing mode. The tracker will swing east and west. And the most dangerous or the most sensitive mode is the first mode, which is the torsional mode. And looking at the animation on the right, you will find out the tracker is very sensitive to the 0 degree position. Once the tracker is stone at 0 degree, and the wind hit the tracker, the deformation of the structure and the velocity and the vertex of the wind will create a phenomenon to let the tracker twist and cannot stop. That is called instability. And if we look at the this map is called the critical wind speed map. It dedicates that each tilt of the tracker has its maximum stable velocity. So the 0 degree has the lowest stable velocity, the critical wind speed. That means the 0 degree is controlling the safety zone of the whole tracker design. And if we are talking about two different trackers, let's make an example. If we have two trackers, right? One tracker is a high critical wind speed, another tracker is a low critical wind speed. We will find that the low critical wind speed tracker will need to go to the stone mode more frequently than the other tracker. That means, for example, if the critical wind speed of this tracker is 9 meters per second, and there's lots of time that the wind speed is higher than 9 meters per second, so tracker need to go to stone. And once the tracker is in the stone position, it cannot output the energy in the normal way, and there will be a lot of energy loss because of low critical wind speed. But if we look at the high velocity, high critical wind speed tracker, there may be only 1 hour in a day that the tracker need to go to a stone position, and the loss of energy will be smaller than the low critical wind speed trackers. That means if we have a higher critical wind speed of the tracker, we will got the better performance of the project. Okay, so what is the parameter that impact the critical wind speed? We understand that if we want to have a better performance, we need to increase the critical wind speed of the tracker. And looking at this two formula, you understand that the critical wind speed is first of all, the critical wind speed is proportional to the tracker frequency, the stiffness of the tracker. And the tracker frequency is inverse proportional to the length of the tracker. Okay, that means if the tracker is longer, okay, the L increase, the frequency of the tracker will reduce, and we have a lower critical wind speed. So we need to change the length of the tracker for the traditional tracker design. However, if we compare the old panel size, which is 350 watt, that is a 90-meter long tracker. If we compare to the old size of the panel, and the old design of the tracker has 18 meters per second critical wind speed, and if we increase the width of the panel, that means we increase the length of the tracker, and the critical wind speed will reduce. Looking at this tracker, that is a 210 cells panel, and the whole tracker has 162 meter long, and that means the critical wind speed has been decreased by 50%. And that will the tracker will not be stable at a certain level, and it will go to stone position very frequently in the days. Means the tracker cannot be operate normally. So that is a very big problem for the tracker design. Okay, so the third challenge is the high stone tilt. Well, we have two pictures to indicate that how the panels will how the large size panel will be damaged in at the field. So the first one is called the crush, glass crush. The glass is damaged, and it has more crush and the panel crush. And the second is the frame bended. Okay, the frame itself, like aluminum frame, is bended because of the high bending moment on the panel. This is very normal. I have to say, this is very normal in current tracker industry, and this is very normal for the tracker that stone at a high tilt. The reason why it become normal and normal, because for the old size panel, the critical map is like this right curve. But if we increase the size of the panel, the critical wind speed map will will be something like the dash line of dash curve of this one. That means if we have the same project, we will have the same project requirement of a wind speed. Before, the tracker will go to 30 degrees stone and everything will be okay. But now it need to go to 55 stone tilt. That means the stone tilt increase, okay? And if the stone tilt increase, the pressure on the panels will increase as well. I take a curve from our wind tunnel testing. That is the data of wind pressure on the panel. So before, if we are talking about 2400 Pascal according to IEC, and before the tracker is stone at 30 degree, the pressure is 24 Pascal, right? But now the tracker need to stone at a higher tilt, 55 degree. The pressure will become 3000 Pascal, and that is 27% increase. 27% increase. Okay, so it means that there will be 27% more load on the panel for the traditional tracker. Let's look at the IEC code. Okay, the IEC 61215 is the code for verify the panels. And according to IEC, there's a formula that the testing load divided by a certain safety factor, well, in the code that is 1.5, okay? And we got the design load. And that is not the end. We have to compare this design load to the SLS load, which is the requirement of the project. The different project has different requirement. So for example, if this one, if the requirement of the project is let's say 2000 Pascal, right? 2000 Pascal, and we have done IEC testing, and we found that the testing load could be 2400 Pascal, and we will see that is okay, right? Because 2400 Pascal, the capacity of the mechanical load of the panel is higher than the requirement of the project. But if the requirement of the project increase to 3000 Pascal, then that is not okay, because the capacity of the panel mechanical load is lower than what is required in the project, and that will cause the damage, the crash of the glass and the bending of the panel. Okay. However, in the IEC code, the IEC MQT16, it is the mechanical load testing. We use most of the panel supplier. They use the setback to simulate the wind load, and the setback is putting on the panels uniformly, right? Like what I simulate here. So all the load on the top of the panel is uniform, right? This is the requirement of IEC testing. But what is the reality? If we look at the animation of this animation, you will find out the wind load itself is not uniform on the top of the panels. On the bottom of the panels, we call the leading edge. On the leading edge of the panel, the pressure will be much higher than the top of the panel. So the simulation of the wind load, the reality is a non-uniform load. Okay, and I listed two pictures to compare the reality and the MQT16 testing. So MQT16 testing, according to IEC, they use uniform load, and this is the bending diagram on the frame, on the panel frame. However, the reality is non-uniform, right? It's not a uniform load. So the bending diagram on this point is very high. It's very high. So that causes a lot of damage on the field. A lot of panel frame damage on the field is because of uniform, the reality of wind load. This is very important, and they has come to bad news, right? So the FEMA, the International Building Code, they want to increase the risk category of the solar power plant. So before, the risk category of the solar power plant is category 1, and that means 300 years MRIS wind speed, the return period wind speed. But now they require to increase the risk category from 1 to 2. Okay, that means the so first of all, the MRIS is changed from 300 years to 700 years, and that means the wind pressure increased by 15%. 50%. Remember what we have done before, right? We done 2400 Pascal according to IEC code. But if this new IBC code published in the public, the wind load need to be increased 15%, and we are talking about not 3,000%, but 3,415% Pascal on the top of the panels. That is 60% increasement of the panel size, of the panel pressure. Okay, so there are lots of the challenge of the large size panel, but is there any solution for the tracker supplier to solve the issue? Yes, the answer is yes. We have the right product to match the large size panels. That is our SkySmart 2 and the Skyline 2. Okay, so let's do a summary. What is the challenge of the large size panel? So first of all, since the size of the panel change, we have to do a new wind tone testing. And then, since the tracker become longer and longer, it has the lower stability and a lower performance, right? And the pressure on the panel size, is very high. The wind load is non-uniform, and there will be there will be a higher wind panel pressure, and the whole tracker area will increase. So the load on the tracker will increase as well. Right. This is a two tracker production line of Arctech. For the 1P system, we call the Skyline 2, and to the 2P system, we call SkySmart 2. SkySmart 2 is launched in 2019, and Skyline 2 is launched in 2021. Okay, so why we want to do this two product? If you're familiar with Arctech, you understand that the two product has the same architecture, that is called a multi-drive system. Before, the whole tracker is only one swing drive, and now they have at least 3 swing drive on the two trackers. So why we want to do that? We have done lots of wind tone testing, and that functionality we done the traditional tracker design is our first generation of Sky Smart, and this is a single drive tracker, and we have done a new tracker product Sky Smart 2. This is a multi-drive tracker, and this is the result of these two trackers. So for the single drive tracker, the critical wind speed map is something like the Z curve. Okay, the lowest critical velocity is at 0 tilt. Okay, and for the next generation tracker, Sky Smart 2, the multi-drive tracker, the critical map is kind of A curve. The 0 degree has the highest critical wind speed. What is the difference for these two one? The difference is, the Sky Smart 2 will have a much higher safety zone than the Sky Smart 1. Means this multi-drive tracker will have a higher, operation wind speed than the single drive tracker, and that will increase the operation wind speed, and means that the tracker will not go to the storm position very frequently, right? And that will bring a lot of additional, performance of the project. And also, since the multi-drive system, they have the highest critical wind speed at 0 tilt. So this is a very, very easy for the tracker to storm at the 0 degree. And once the tracker storm at 0 degree, compared to the tracker that is storm at the high tilt at 55 degree, you will find the 0 storm, tilt tracker has a less wind pressure than the 55 degree when high tilt, and that will about around the 60% compared to the traditional tracker. That means if we have deployed the Sky Smart 2 or Skyline 2 tracker, the pressure on the top of these two trackers will have a 60% lower wind pressure than the traditional trackers. That is helping the panels to reduce the possibility of the damage. Okay, let's do the summary of the multi-drive versus the single drive. So the multi-drive system will have the lower wind pressure on the panels, right? Before we're talking about the 3,000 Pascal, but now it's only 1,000 Pascal. It's 30% of the traditional trackers, and we will have the high operation velocity. That means the higher performance. Okay, that will bring a lot of additional energy of the project. And since the safety zone is higher than the single drive, the tracker itself is more stable. Okay, and we will have a shorter foundation. That means we will have a lower installation cost. So all the Sky Smart 2 and the Skyline 2 product, we have done lots of third-party verification, and we got this certification from our partners. This is what we have currently, and we got the Adafa 2.1 gigawatts, which is the biggest single solar power plant which use our Sky Smart 2 tracker, and it is on the Abu Dhabi and going to finish right now. It's under construction and going to finish. Right, that's it. So I'm John Smart from Arctech Solar. If you want to have more questions, you can contact me by WeChat and LinkedIn. Thank you all.